You know, usually when we think about a supercomputer, there is this immediate mental image of massive humming infrastructure.
Like endless rows of server racks.
Exactly. Just this freezing cold, heavily air-conditioned warehouse, basically consuming enough electricity to power a small city. We inherently associate, world-changing computation with massive physical scale.
Yeah, it's a very industrial mindset, really.
For sure.
We've been trained to believe that to solve the biggest biological problems on Earth, you have to centralize your power. I mean, you had to send your data off to a server farm somewhere
Yeah.
and just, well, wait for the results.
But then you look at what is happening right now at the very bleeding edge of AI and computational biology, and suddenly that warehouse isn't strictly necessary anymore.
No, not at all.
We are looking at a paradigm shift that completely upends the scale of discovery. So welcome to today's deep dive. Our mission for you today is to unpack a very specific, honestly almost unbelievable stack of new research to figure out how exactly do you transform an ordinary everyday smartphone into a localized supercomputer.
One that's capable of autonomous drug target analysis, no less.
Right, which is wild.
It definitely sounds like science fiction at first glance.
Yeah.
But, the architectural synthesis to do this is actually already here.
Yeah.
And it relies on completely rethinking how we process data.
So we've got a brilliant stack of sources to guide us today. We are pulling from breakthrough research papers on a deep generative framework called Transferable Implicit Transfer Operators.
Or TPIO for short.
Right, TPO. And we are also looking at the hierarchical reasoning model, extreme data efficiency through something called polymath learning. And finally, the architectural synthesis of all these pieces, which they call the sovereign edge.
It's a lot to cover.
It is. And to you, listening right now, if you've ever wondered why discovering a single new life-saving drug takes, decades and costs billions of dollars, a huge part of that comes down to computational bottlenecks.
Exactly.
Today, we are exploring how AI is taking that massive data center level computing weight and basically shrinking it down so it runs right in your pocket.
Yeah, and to really appreciate the elegance of this localized solution, we first need to look at the mathematical wall researchers hit when trying to simulate biology.
Right, the bottleneck.
Historically, if scientists want to understand how a potential drug interacts with a target protein in the body, they use molecular dynamics simulations.
Okay.
They're essentially writing mathematical equations to simulate the physical movement of every single atom over time.
Which, tracking every atom in a biological system sounds computationally heavy just on the surface. But the real issue is the timescale, isn't it? The sources talk about the necessity of taking these femtosecond steps.
Yeah, femtosecond, which is 1/1,000,000th of a billionth of a second.
That is, I can't even wrap my head around that.
Right, it's absurdly small. And the reason traditional simulations have to move forward in those excruciatingly tiny increments is purely for numerical stability.
Meaning, like, if the mathematical equations try to jump too far ahead in time, they completely break down.
They shatter. I mean, atoms vibrate incredibly fast. If your simulation tries to guess where an atom will be even 1,000th of a second from now, the margin of error multiplies instantly.
Oh, wow.
Yeah, the simulated atoms might, clip into each other, the energy calculations explode, and the simulation just crashes. So to keep the math stable, you are forced to calculate the physics 1/1,000,000th of a billionth of a second at a time.
Okay, let's unpack this with an analogy, because the biological processes we actually care about, like a drug detaching from a protein or, a complex protein folding into its functional shape, those do not happen in femtoseconds.
No, not at all.
They unfold over nanoseconds or microseconds or even full seconds, right?
Exactly.
So simulating a full second of biology using femtosecond steps is like trying to map out a cross-country road trip from New York to LA, but you're only allowed to measure your progress like one single grain of gravel at a time.
You would spend years just getting out of the driveway. And that scale mismatch is exactly why identifying hidden conformational states of proteins, these slow, rare events that dictate how a drug binds, is so computationally crushing.
Because it just takes forever.
Exactly. If we want to run this kind of analysis on a smartphone, we cannot just build a slightly faster engine to count the gravel. We have to figure out how to fly over the road entirely.
Okay, so we are stuck in the gravel. Our math will blow up if we try to jump ahead, and we obviously don't have a server farm to brute force it on a phone. So what's the alternative? This is where the research introduces that deep generative modeling system we mentioned, TITO.
Yeah, TITO is fascinating.
It completely bypasses explicit time integration, right? It stops trying to calculate every step.
Exactly. Instead of advancing the dynamics through billions of tiny steps, TITO learns the statistical rules of molecular motion across different, much larger lag times.
Okay.
So it draws direct statistical samples of how an atomic configuration will evolve over an arbitrarily long leap in time, like nanoseconds or microseconds, all in one go.
The sources mention it uses something called a continuous normalizing flow to do this. For those of us who don't have a PhD in fluid dynamics or advanced statistics, what does a continuous normalizing flow actually look like in practice?
Think of a lump of clay.
Okay, clay.
In its raw form, a simple sphere of clay is very easy to measure and understand mathematically. Now, a complex molecular state, like a uniquely folded protein, is like a highly intricate finished clay sculpture.
Got it.
A continuous normalizing flow is basically a mathematical process that learns the exact, smooth, reversible steps to mold that simple sphere into the complex sculpture.
Oh, interesting.
Yeah, it uses an ordinary differential equation to transport a simple, easy-to-sample distribution into the highly complex distribution of molecular states.
So by using that transformation, TITO doesn't have to calculate every single vibration of every atom along the way. It just maps the starting point directly to the destination.
Right, and the resulting speedup is just monumental.
I bet.
By eliminating that step-by-step integration, TITO accelerates molecular sampling by up to 15,000-fold.
Wow.
Yeah, this allows localized mobile hardware to achieve a massive simulation throughput of roughly 10 milliseconds of physical simulation time per day of compute, which is unheard of for edge devices.
Okay, wait. Here is where it gets really interesting. But I have to admit, my skeptical alarm bells are definitely ringing a bit.
Fair enough.
If TITO is just leaping through time and molding distributions, isn't it just hallucinating physics? I mean, how do we know it's not breaking the fundamental laws of thermodynamics just to give us a fast answer?
The researchers had to prove the system wouldn't do exactly that. The underlying safeguard here is that TI2 preserves what is known as the Boltzmann distribution.
The Boltzmann distribution, meaning what exactly in the context of our simulated biology?
The Boltzmann distribution represents the natural physical equilibrium of a system based on its energy and temperature.
Okay.
Imagine rolling a marble into a bumpy bowl. Gravity will naturally pull it toward the deepest valleys, but occasionally it might get bumped into a shallower ridge.
Right, depending on how hard it rolls.
Exactly. The Boltzmann distribution dictates the exact mathematical probability of where that marble should naturally settle over time. TITO is mathematically constrained to respect those probabilities.
Ah, I see.
It isn't just drawing plausible-looking protein shapes, it is drawing physically accurate states that obey real-world thermodynamics.
And because it models those long lag dynamics directly, the sources show it can quickly explore and uncover what they call metastable basins.
Yes, the hidden states.
Right, if I'm understanding this, a protein is like a complex piece of origami. It might spend most of its time folded into one shape, but occasionally under the right conditions, it snaps into a completely different shape. That rare shape is the metastable basin.
And that rare shape might be the exact vulnerability a drug needs to target.
Wow.
Traditional MD simulations, because they take those tiny femtosecond steps, they get trapped. They fall into the most common molecular shape and just vibrate there for billions of steps, completely missing the rare conformational changes.
The research actually highlights a glaring example of this with a molecule called propiolamide. A traditional simulation ran for 36.5 nanoseconds, which is an eternity of compute time for that method, and it completely missed a crucial metastable basin.
Just completely skipped over it.
It never saw the molecule change shape, but TITO, running significantly faster, leaped right into that hidden state, and ultra-long reference simulations later confirmed TITO was dead on.
The validation is definitely there, but the most crucial element for our edge device isn't just speed, it's flexibility. TITO features zero-shot transferability.
Because a smartphone operating on a nightstand can't pause to download a new multi-gigabyte training dataset every time it wants to analyze a different drug candidate.
Exactly. It has to generalize from what it already knows. TITO is trained to generalize across different chemical compositions and temporal scales.
Which is pretty amazing.
It really is. It can actually evaluate novel drug targets on the fly and even extrapolate its physics predictions to peptides that are twice the size of anything it saw in its training data.
So the physics engine is sorted. TITO handles the simulation, skipping the microscopic steps without violating thermodynamics or, burning down the phone's battery.
Right.
But a physics engine is ultimately just a calculator. Who is pressing the buttons? How does the smartphone actually understand multidisciplinary biology well enough to plan a complex scientific experiment?
The intelligence directing the simulation is governed by the cognitive architecture of the sovereign edge device.
Okay.
The foundation is a mixture of experts model. Specifically, the sources cite the use of Gemma 4, which is a 26 billion parameter model.
See, 26 billion parameters sounds like a desktop melting amount of processing power. How does that squeeze onto a mobile chip?
That is the beauty of a mixture of experts architecture. Even though the model holds 26 billion parameters of knowledge, it does not use them all at once.
Oh, really?
Yeah, it only activates an incredibly lean 3.8 billion parameters during any single inference step.
Okay, that makes more sense.
Imagine a massive corporate office building. You don't need the accounting department, the marketing team, and the legal team all working on the same single email.
Right.
The model routes the computation only to the highly specialized expert neural pathways needed at that exact millisecond.
That solves the processing weight, but we still have a massive data problem. Training large language models to understand complex science usually requires feeding them terabytes of data. Millions of research papers, endless chemical libraries.
Normally, yeah.
How does a localized model learn all of this biology and physics without that massive server-level data set?
Well, the researchers utilized a framework called polymath learning. It operates on extreme data efficiency. Instead of feeding the model an entire library, they discovered they could elicit broad, cross-domain reasoning capabilities using a single, strategically synthesized training sample.
Okay, I have to push back here. It learns from one sample.
Just one.
That sounds overdramatic. I mean, you can't just teach an AI one single chemistry problem and expect it to suddenly understand the broader universe of biological interactions. That's like reading one page of an encyclopedia and knowing the whole universe.
It definitely defies how we traditionally view machine learning, where volume is basically everything. They call this single sample the synthetic prime metasample.
Synthetic prime.
It is a highly engineered, densely packed problem that forcefully integrates physics, chemistry, biology, and mathematical optimization all into one cohesive puzzle.
The sources outline the exact question used in the synthetic prime. It asks the model to calculate the minimum number of 400 nanometer photons required to supply exactly enough energy to dissociate all the hydrogen bonds in a specific DNA fragment.
Right. And to solve that single puzzle, the model cannot just regurgitate memorized facts. It is forced to understand the strand sequence and base pairing of biology.
Because it's DNA.
Exactly. It has to understand the chemical bonds and dissociation energy of chemistry. And it must apply the photon wavelength equations of physics.
But the sources point out an incredibly surprising underlying mechanism for why this works. The efficacy of learning from this single sample correlates heavily with salient math skills, specifically algebra and precalculus.
Yes.
Why does being good at algebra suddenly unlock complex biology and physics?
Because algebra is a foundational reasoning mechanism. To master algebra, a model has to understand variable abstraction, logical flow, and constraint satisfaction.
Oh, I see.
It is like teaching someone the fundamental rules of chess. You don't need to show a new player every single chess game ever played in history. Once they deeply understand how the knight moves and how the board is constrained, they can apply those rules to any new board state they encounter.
That's a great way to look at it.
When the model masters abstract mathematical reasoning through the synthetic prime sample, that capability transfers. It allows the model to grasp thermodynamic principles intuitively without needing massive, domain-specific data sets.
It learns how to reason rather than just memorizing what to know. That is brilliant.
It really is.
But knowing the science is still only half the battle. If this phone is going to act as an autonomous laboratory, it has to generate the actual code to run the experiment. It has to plan out long sequences.
Well, that which takes logic.
And if anyone has used a standard AI model to write complex code, they know the model uses chain of thought. You ask it a question, and it spits out 3 paragraphs of text explaining its reasoning step by step before it finally gives you the code.
And on a mobile device, chain of thought is a fatal flaw.
Because of the memory.
Exactly. Standard LLMs generate a massive amount of tokens when they think out loud like that. That constant text generation would immediately fill up the mobile device's context window, the active memory it uses to keep track of the conversation, and the phone would just crash.
You can't plan a 20-step chemistry experiment without thinking through the steps, but the model isn't allowed to talk. So how does the sovereign edge architecture solve the memory drain of planning?
It replaces chain of thought with the hierarchical reasoning model, or HRM. Yeah, HRM operates entirely without explicit text generation. It relies on latent reasoning within its hidden states.
Latent reasoning, so it's thinking, but it keeps its internal monologue completely hidden in the math rather than generating text tokens.
Exactly, and it does this with remarkable efficiency. The standard transformer architecture of most large language models is paradoxically shallow. It has a fixed depth, which limits its ability to loop back and perform deep algorithmic reasoning.
Okay.
HRM splits the workload using only 27 million parameters. It sets up a high-level module responsible for slow, abstract planning and a low-level module that handles rapid, detailed computations.
A fast loop and a slow loop.
Exactly.
So the slow high-level module sets the overarching goal for the chemistry experiment. The fast low-level module loops repeatedly, trying to solve that specific step, reaching a local equilibrium.
Right.
Then the high-level module assesses the result, updates the plan, and gives the fast module its next task.
And it completely avoids the trap of standard recurrent networks that often converge too early and stall out. The sources show this tiny 27 million parameter HRM achieves near-perfect performance on tasks that completely break massive chain-of-thought models.
Wait, really? Like what kind of tasks?
Well, it can solve complex Sudoku puzzles and find optimal paths in 30 by 30 mazes natively inside its own hidden states, with zero text generated.
That's bonkers. So our edge device can now plan complex logic without blowing out its RAM, but we have a glaring safety vulnerability remaining, which is hallucinations.
Always a risk.
What happens if the HRM plans a brilliant experiment but hallucinates a fundamental physical constant? Or generates invalid syntax for the simulation?
Yeah.
If you are designing life-saving drugs, you can't have the AI deciding that the speed of light is slightly faster today just to make the mathematical constraints fit.
No. Factual grounding is absolutely non-negotiable here. Normally, enterprise systems solve this by using a massive cloud-based retrieval augmented generation system, or RAG, to constantly look up facts on the internet. But a core tenet of the sovereign edge is that it can operate autonomously off the grid.
Enter GraphMERT. The sources describe it as an 80 million parameter encoder-only model. How does GraphMERT actually keep the physics grounded without an internet connection?
GraphMERT acts as a local neural-to-symbolic converter. Instead of just predicting the next most likely word like a standard LLM, it distills explicit knowledge graphs from unstructured text. It enforces strict symbolic rules.
Oh, I see.
If the language model tries to pass a constraint to the physics engine that violates a known thermodynamic boundary, GraphMERT acts as the reality check. It ensures the generated scripts strictly adhere to valid, domain-specific physics.
So let's look at the full picture of the device, because the way this loop closes is wild. The smartphone understands the broad science via polymath learning from a single synthetic sample. It plans the multi-step experiment silently in its hidden states, using HRM. GraphMERT sanity checks the physics. Then, instead of using a traditional server-dependent integration engine to run the simulation, it uses TITO to execute the physical dynamics, leaping across those femtosecond gaps.
The execution is flawless, yeah. But an autonomous laboratory isn't truly autonomous unless it can learn from its mistakes.
Good point.
It has to evaluate the results of the TITO simulation, update its own code, and try again. It basically has to update its own neural weights locally.
And doing that requires backpropagation. Standard backpropagation, how a neural network learns, scales linearly with time.
Yes, it does.
If a simulation runs for 10 hours, the memory needed to store the history and learn from it also takes up 10 hours worth of space. That bloat would kill a phone.
Absolutely. To solve this, the architecture uses the Darwin-Gödel machine framework, utilizing something called attention residuals, or at-res.
At rest, okay.
Instead of storing a massive linear history of every single calculation, at-res uses learned selective attention.
How does selective attention bypass the need for history? Like, how does that work?
Think of it like human memory. When you touch a hot stove, your brain doesn't record a high-definition 4-hour video of the entire kitchen leading up to the mistake.
Right.
It extracts the crucial lesson, the stove is hot, and discards the raw footage.
Oh, that makes total sense.
And at-res selectively retrieves only the necessary context across the network's depth. When combined with HRM's unique architecture, the backpropagation memory footprint is reduced to what computer scientists call big O of 1, constant memory.
Constant memory. Meaning, whether the simulation runs for 10 seconds or 10 days, The memory requirement to learn from it never grows.
Exactly.
It stays completely flat. That is the holy grail for mobile processing.
It allows the smartphone to stably compute gradients and recursively improve its own scientific capabilities indefinitely, using only its local, limited RAM.
We have just unpacked a stack of technology that entirely bypasses the need for supercomputer clusters. TITO skips the excruciatingly tiny steps of molecular dynamics without breaking thermodynamics.
Yep. Polymath learning imparts multidisciplinary knowledge via algebra. HRM plans the experiment in a latent space without context bloat. GraphMERT grounds the physics in reality. And attention residuals allow the device to learn from its experiments with a flat memory footprint.
It's an incredible stack.
You have literally turned an everyday smartphone into a real-time, atomistic resolution drug discovery engine.
And as we look at this synthesis, it pushes us toward an entirely new horizon for computational biology. The sovereign edge proves that localized devices can autonomously map complex biological landscapes.
Which leaves us with a truly fascinating question to ponder. If all of this processing can now happen locally, entirely off the grid, it completely changes the privacy model of healthcare.
It really does.
If you don't need to send massive data sets to a cloud server to run these simulations, what happens when this technology is applied to hyper-personalized medicine? Could the edge device sitting on your nightstand take a local swab of your specific individual DNA sequence and autonomously run molecular dynamics simulations to tailor a drug compound precisely for your unique genetic makeup, all while guaranteeing your biometric data never once leaves your physical possession?
Decentralizing the computation means decentralizing the discovery. The implications for secure, personalized medicine are, honestly, profound.
Next time you pick up that little rectangle of glass and metal, just remember, it is no longer just a communication device. It has the architecture to be a sovereign, autonomous laboratory. Thank you for joining us on this deep dive. Keep questioning the limits of the technology in your hands, and we'll see you next time.